That's what I was thinking. I was like, I really can't read this. We don't have to use it. Whatever.
Oh, there's nothing new just yet. That's from, yeah. These were from Wednesday. Anybody that wasn't here Wednesday? Wanted to hand out, yeah. I like to try to get rid of all the handouts. I want to go to recycling. I'll keep this in again in a year, but then I might change the handout. Okay. Keep going. All right. So we're looking ahead now to the first exam, which is on next Wednesday. So Monday in class will be a review day, and we'll go over some practice problems, have time for questions. There's no homework due next week, so just focusing on reviewing the material to this point and getting ready for the exam. Right? Today in class, we could ask some questions about homework 4, but we'll look at some other examples too to kind of contrast and compare some of the different types of questions. One challenge with the exam is, besides doing the problem that's asked, is figuring out what type of problem it is. Right? Is it asking about binomial? Is it asking about Poisson? Is it asking, something else? I'm kind of getting used to the style of the questions that are there. So there are a number of practice problems that are posted, right? So under the exam link, here are some different practice problems. I actually have 3 sets because I taught different versions of statistics, or this biostatistics class in these past. So these are some past problems that I've written and asked about this material. So I think it should give a style of the type of things that you would see. So the plan for Monday will be to go through some of the questions from this first one here. And so I'll kind of start off with that. It doesn't mean we have to be limited to that. You could ask about ones from the other ones, but I'll start doing that, right? And one virtue of having multiple kind of sets of these things is one thing what I recommend is review what's in lecture, what's on the homework, what's in notes, some material in the book, and see if you have kind of an understanding of the topics and where you might have questions, and then try one of these exams, right? And if you try the exams, as exams, can you, based on what you know, sit down and write out solutions and write out numbers? Then you can compare it to the answers and see how well you do. Is it different than that? And I'll get some solutions posted for these shortly. I have a few drafts of those. I don't, but those will go up pretty soon, so you'd be able to look at those, right? If you simply wait for the solutions to come and then Tuesday night before the exam read through the solutions, it might seem like it makes a lot of sense, but it's a little bit different to actually be writing it down on a piece of paper or reading the problem and figuring out what type it is. Right? So there's multiple things that you could do. So since there's essentially 3 of these, so you could do one early, right? And then save a couple for kind of further checking. And again, we'll go over the first one that's there, right? And so these are under assignments. There's links for the exams, and so you could be able to find that there. I thought I was going to get the homework 3s back, but the grader didn't. I did not receive them, so I think she's bringing them later today. So try to get back graded material on Monday, so you see what your papers are. I'll get solutions posted, so you can look at those things for studying. So sorry that your work isn't back right now. I can't quite do anything to make that up right now, but hopefully we do get back on track with that. And to the plan for today, is there anything else to look at? That's that one. The homework 4 is here. And this one was just under the exams. There's that link. Go to that one. So the plan today is to go over some problems and look at different different scenarios and see how different topics might be asked in slightly different ways that'll change how it's answered. But before we get into those, are there any questions about? All right, we'll look at some problems and ask questions as we go along. So here's the first scenario. Right? Here's the example. One. So say in a population of fruit flies that 30% of them have a mutation that makes them black in color, whereas the other 70% are gray in color. And you catch 14 of these fruit flies. What's the chance that you get less than 4 in your sample that are less than 4 that are the black color? So what is the probability? Less than 4. The black fruit fly color. So what do we know based on this? And how would we go about answering the problem? So less than 4, what does that mean?
Every other possibility that's lower than 4.
Yeah, so which
2,
one?
1, 2.
Yeah. So less than 4. All right, it's going to be 0, 1, 2, and 3. So if X is the number of fruit flies that have the black coloring, like probability X equals 0, plus the probability X equals 1, plus the probability that X equals 2, plus the probability that X equals 3. We add together those 4 probabilities, and that'll be the chance that it's less than 4. Right? And how can we calculate any of these probabilities? So say I asked you, focus on this first one, the probability that is 3. So we get 3 of our selected 14 flies have this black coloring. Does this look like any of the distributions we've used? Yeah.
Would you do the 0.3 to the third and then the rest 70%?
Yep. So there's 14 flies. If we ask what's the chance that it equals to 3, the probability that it has, each one has this black coloring is 0.3. Right, so it's 0.3, and we're asking about 3 of them. Was it 0.3? Yeah, it was 0.3. And then 1 minus that, or the 0.7. And so there's 14 minus 3, or 11 there. But we don't really care whether it was the first 3 that were that color or the last 3 or any other things. We have a combination thing in the front. We have to count the number of ways we can get 3 and 11, which is split between these colors. Does anyone know what the combination symbol was? 14. 14 choose 3. Yeah. How do we choose 14 choose 3? Fourteen flies. You gotta label 3 of them.
14 times 13 times 12, 3 times 2 times 1.
Yep. We have to put 3 labels on there. 14 choices for the first. Say that's fly number 7, and then 13 choices, fly number 6, and then another choice is fly number 1. And those would be 3 flies that have that color. We don't really care which order we did it in. As long as you have those 3 flies, it would be fine. So you can reorder those and still get the same thing. So that would be the answer. So that's 14 times 13, and that's 6. So there's a 2. So 28 times 13. I can't do that in my head very easily, right? But that would be the answer. So 14 choose 3. Let's put this on do it on the computer real quick. If you had your calculator, we would, there it is. So we had this as a calculator. Edit a view, zoom in a little bit, make it bigger. We just need to calculate this, right? 13 times 12 times 11, divide by 3 times 2 times 1 is 286. So we need the 286 times our 0.3, and there's 3 of them. Yes.
Wasn't it 14, 13?
Oh, 14, yeah, sorry. 14, 13, and 12. So it should be, yeah, 364, sorry about that. 364 times 0.3 cubed times 0.7 is the 1 minus, and there's 11. So you get exponents with little raising things. So 19.4%, 0.194. So if I'm thinking about R as my little calculator here, I would have to type in enough to do that. 364.194. So this thing is 364, and the final answer is 0.194. All right, so that's the chance that x equals 3. You get 3 of them. What's the probability that x equals 2? 2 of the flies out of 14 have this coloration. So it follows kind of the same pattern, right? 0.3, yes. 0.7, there's 12 then that are no. And we need 14 choose 2. The 14 choose 2 minus 14 times 13 over 2 times 1, so that's 7 times 13, that's 80, that's 91. So 91 times the 0.3 squared times the 0.7 to 12, and that ends up being, if we calculate that one, so 14 times 13 over 2 is the 91. So 91 times the 0.3 squared times the 0.7 raised to the 12, 0.11, 113. 0.113. If we have just 1, right, we have to choose 1. There's only 14 choose 1 is just 14. 1 of those and 13 that are gray, it's 0.00 or 0.41, rounding a little bit. And if it's none of them, it's just 0.7 to the 14, right? They're all none. There's only one way that can happen. The chance that they're all that is 0.007, right? For those probabilities. So, answer this question, the probability that there was 2, 0.113, the probability that x equals 1 of these is 14 choose 1. 14 choose 1, that's just 14. 14 over 1, or just think about, what does it mean to choose one person out of 14? Well, there's 14 choices, so that's the number. 0.3 to the first, 0.7 to the 13th, and that one ended up being 0.041. And then the chance that you get none is just 0.7 to the 13th, so that's 0.007. So the chance that we're at 0, 1, 2, or 3 is we're just going to add up the different probabilities. And the chance that you're more than that is just 1 minus that stuff. So instead of having 14 flies, say you had 140 flies. And again, the proportion that are the dark color rather than the gray color is 0.3. How many out of this sample would we expect to be the dark black color?
$42.
42, 140 times 0.3, then all that n times p in the symbols we use for these things. And so 42. Yep. So what do you expect 42? How many do we expect to be gray? Changing those two words from the sample. 98, right? So 140 minus the 42 is 98. It's also 140 times the 0.7 is 98. So that's how the split we'd expect. What's the standard deviation of the number we should see? Will we get at least 30? Maybe you need a certain number to do an experiment. Would you get at least 30 by sampling this way? We expect 42. You could calculate all the probabilities, but this is big enough that we can kind of do the plus or minus 2 standard deviations to figure out what's likely. So binomial standard deviation, right? There's an n times p times 1 minus p for the variance. And the square root of that was the standard deviation. So 140 times 0.3 times 0.7, and the square root of all that. The average is 42, so 0.7 times that is 4, 28, 29, 29.4. Right. And the square root of that whole thing was more than 5, not quite 6. And we have a calculator to go over here. So just square root of, we did 140 times 0.3 times 0.7, about 5.4 as a standard deviation. And this average up here is 42 flies. So are we sure that it's going to be over 30? It's probably going to be over 30. Right? You take the mean minus 2 standard deviations. So you don't often get much less than that. You could, right? Just by random chance, but it's not that likely. Are you going to get over 36? Maybe not. Right? It's going to be a non-trivial chance that you're going to get 35, 34, 33, something like that. You might also end up with 50 something, right? A little bit more than 50. So that's binomial mean variance. So this has been an example of binomial. Let's think about doing it a different way. Suppose you sample until you find a black fly. Sample until you find a black fly. How many flies do you have to catch? Well, maybe if it's something you can see, you can visually pick out which ones sample, so it's a little bit more efficient. But if it's something, genetic or some characteristic you couldn't really tell until you actually had the thing, right? Or you couldn't be that specific about it. Maybe you have to catch them and then determine is that their coloring or other characteristics of them, the male, female, to determine whether it is. How does this differ from the We don't know how many times there are, right? We're just gonna keep going as long as we need to go. And there's not a fixed upper limit, so it's not binomial. So how many flies do you have to catch? We might have to catch 1, 2, 3, et cetera. It doesn't have a limit. So at that point, right, it's not binomial. So don't use the binomial formulas to make that work out. Probability that you have to pick just one fly and get it. That's 30% each time, minus 0.3. The chance that you have 2 flies would occur if you get a gray one and then a black one. 0.7 times 0.3, 0.21. The chance that you have to get 3 flies, 0.7 squared times 0.3, you get 2 gray, and then you get your 1 black fly. There's no combination in the front of this because we're just, we really are just kind of sampling through time. They're all gray, and then that one is the black one. So there's no extra combination thing. So 0.7 times that is 0.147. The probability that it's 4 that you have to take is going to be 0.7 cubed times that. So 0.7 times this one is 49, 4, 28, 32, 33, and 7, 10%. And so on. So this one, we call this a geometric distribution. The probability T equals 0.3. So if it asked about 5 or more trials, then you're going to add these up and take 1 minus. Or with the chance that it's 4 or less, we're going to add those up. And so 0.5, about 0.75 or so if you add those 4 things up. So about 3/4 of the time you're going to get values. You're taking 4 flies, but 25% of the time you're going to do more. Right? What's the expected number that you're going to do? There's a formula for this expected value. How many do you expect? How many do you expect to need to capture? Find 1 black fly. Well, in the geometric, the mean of the number here is 1 over p. So it's 1 over 0.3. We're about 3.33 flies, right, on average. You don't have to round that to an integer, to 3 or 4. You don't have to round it. It's 3.33. Sometimes you do more, sometimes you do less. But if you imagine the scenario of going out for a big population of flies out in the swamp and trying to catch them and identify them, sometimes you get 0, 1 or 2 or 3 or 10 before you find the next one that's that color, that special case, that special genetic case. And then, but over the long run, the average number of times you're going to have to do it is 3 1/3 to get 1. But any questions? Any questions on homework that you want to go to talk about, or do you want to see another example? Yeah.
The number 4 on this.
On the, number 4 on this current homework?
Yeah.
So let's look at number 4 before we look at other things. So number 4 on this homework was this problem 4.23. Right. So 4.23 in the homework asked, right, so there's 10 gonorrhea cases are reported over a 3-month period among 10,000 people in an urban county. Statewide incidence rates are 50 per 100,000. Good. So statewide is 50 per 100,000. And then our urban center, the population is 10,000 people, and they have 10 cases. And so, the statewide incidence of that is the number of gonorrhea cases in the county unusual for this time period. So this is asking, is the probability of seeing something like this unusual? Is it surprising? If the state rate is really 50 per 100,000, if that really applies to urban. So a lot of hypothesis testing and questions and statistics get asked like this. Here's the state rate. Right? If that rate applies here, is this 10 cases a surprising number? If it's unusual, we might then conclude that the state rate doesn't apply, or there's an infection risk or something going on in that urban area that makes it different. Kind of set up this null hypothesis and then calculate the chance of what we got under it, and if that's small probability, then probably that assumption was wrong. It's kind of this reverse reasoning that we'll go through a lot. Right? So what can you do in this problem? How did people, so 50 per 100,000, we don't have 100,000 in this community, right? We have 10,000. So if it's the state rate, right, and 50 per 100,000, right, then it's 5 per 10,000. Right? If the same comparable rate would happen. These type of problems are often modeled with a Poisson distribution, where the rate, in this case, that's relevant for this urban population, sometimes called lambda, is 5. That's the average number. It's also a parameter, a number that goes into the probability calculation. So things that are a very kind of rare, small numbers out of a very big thing, Poisson often gives very good probabilities. Right? So what's the probability that x equals 10 if it's this Poisson? Right? The Poisson probability formula, there's an e to the negative lambda, lambda to the x, script x here, for x factorial. So what's the chance that we would see 10? Well, if it's 5, then it's u negative 5, 5 to the 10th over 10 factorial. And that 10 factorial is a pretty big number. 10 times 9 times 8 times 7, all the way down to 1. The e to the negative 5 term on your calculator, you might do 1 over e to the 5th. Or if you can put negative 5 into your calculator, take the exponent of that. So this is something to check on your calculator before Wednesday. Right? If you need to calculate a Poisson probability, you need to do that exponent. Right? So scientific calculators, even if they're simple ones, have exponents, and so you could do that. Some of them you type in 5 and then hit the negative to make it a negative number, and then exponent that. Other ones go the other way. You type exponent and then negative and then 5, and so for the exam, in general, you can get partial credit for writing down formulas. And actually, you can protect yourself a little bit from calculator errors by writing down formulas. Right, so if you write down the general formula, fill in the numbers, right, that's a lot of the problem. Then you need to put it into your calculator to get the final number. But if you have the formula right and something goes wrong with the calculation, you'll still get most of the points. If you just write down a number and it's wrong because you read it off the calculator and somehow typed something in, and I don't know how you got it, I can't give you any partial credit. So write down the formulas and you'll get more credit. So what is that in R? I can remember that. I wish this moved, but it's kind of bolted to the floor. So this Poisson business, right? So exponents get done as e to the negative 5, exponent it gets written like that in R5. There's 10 people, and then factorial was a factorial of 10 is a number. And that comes out to be 0.018. The density is a Poisson density function, so I can put 10 in there and a rate of 5, and it gives me that probability. But that's what it's calculating. So actually getting 10 is pretty rare, right? But you know, any number, 9, 10, 5, whatever thing, could be kind of rare if there's a lot of possibilities, right? You've got to spread it over all these. So to answer, is it really unusual, you really want to ask, is it 10 or more? Right? 10, 11, 12, and so on, forever. We don't do that. If you do the, 10 or more, 1 minus that is 0 through 9. Right? So the density, so you could calculate the density if you had 9, and the factorial of 9. The chance that you have 9 is that. The chance you had 8 is that one. Right? The chance that you have 7, and so on is that. So if you kept calculating those, you could add up all 0 through 9 and take 1 minus that, and that would be the how unusual, a measure of how unusual that is. So if you take a sum of the density of a Poisson going from 0 to 9 with a rate of 5, right, you get about 96.8%. So the chance you're at 10 or more, 1 minus that, is about 3%. Right? 1 minus that. So something that happens only 3% of the time is a little bit unusual. And so probably public health officials would conclude that that urban area has an elevated rate, so something's going on there. There might be other factors, right? There might be younger people younger adults living in the urban areas, right, versus the suburbs versus rural. Right? There might be a lot of other social activities going on in that area that would be associated with that, right? So the rate might not be unusual if you adjusted for those other factors that are kind of associated with sexual activity. But anyway, so kind of the answer to is it unusual to have 10 to fully answer that in a statistical sense, we really want the probability that it's greater than or equal to 10. At what we have or greater. This is actually a calculation. This would give something called a p-value. So because it goes on forever, we take 1 minus the probability that it's less than or equal to 9. And if we add up all those 0 through 9, it's 0.968. And so we got 0.032, which is a bit unusual. The probability rate really is elevated there if this is somehow a random. Well, that was 10. Yeah. Well, that was essentially that one. It was this Poisson.
Can you, number 6, algebra.
Number 6. So 4.86. So 4.8, there's this population that has 0, the number of numbers. We randomly sample one individual. What's the probability distribution for that? Let's list out those values. What's the probability of losing 1 through 14? What's the probability at least 1, 2, and so on. So this number 6 here, which is 4.86. That the number of teeth lost and the probabilities of those different things. Right? So the numbers that are possible are 0, 1, 2, 3, 4, and then it gives a range. And it was suggested that you use 7 and 12 as kind of midpoints for those ranges. the other one's 10 and above, so that's not really the midpoint, but it seems, the probabilities, the counts are decreasing as you get up there. So it's a little bit bigger than 10, but not 18 or something. And so what it gives in the table is the number that have that value. So if these are the values of x, it gives the number of zeros, the number of ones, the number of twos, the number of threes, and so on. And then the number in that category for 7, and the number in that category for 12, and those all added up to a certain sample size. So for instance, in 1 is 1,978, and the total is 38,905. Right, so if we randomly pick one person from this 38,000 some, right, the chance that we pick somebody that has one tooth lost. Okay, so you randomly pick somebody from this 38,905, and there's one tooth lost, assuming that it's all equally likely. We're just going to get the number that have 1 over n, which in this case is 1978 over the 38,905. And come up with a probability. It's about like 2 out of 39 or 2 out of 40, is about 1 out of 20, is about 5% or so as a chance. The chance that, say, it's greater than 4, how would you answer that generally? Yes?
1 minus probabilities of it being 0, 1.
You can do 1 minus the probability that it's less than or equal to 3. We can jump from 4 to 3 because it's discrete, right? So here's the divider. Greater than or equal to or less than. But if you have these numbers, right, what's the next step? How do you get those probabilities from those, a table of numbers like that? How many people are less than or equal to 3? I can add up those in 0 in 1, the number of counts that are there in the table. The other way to do this, because it's kind of split in the middle, is you could add up these numbers and do that. So kind of directly, you can do n4 plus n7 plus n12 over the total sample size, or you can do 1 minus, adding up the lower categories, n0 plus n1 plus n3, and dividing that by the sample size. And this is an n12. Let me write that again. So it's n to the 12 subscript. So adding up those numbers. So I like the idea of thinking, either one side or the other. Sometimes one is easier than the other. In this case, it's not too much different either way you go. Right? So in doing this from the R code that was on there, right? These numbers, you could type them into your calculator and do the division. Right? This is the R code that was provided that did some of these things. And this command up here sets up the frequencies. Right? You can just put the code in here, type this run, and it will run that. What it does is then create this vector, this series of numbers called frequency or freq. Right? That has those different numbers. And the sum of those numbers is, oops, is that the right number, 38,905? That's not, yeah, that is, okay, good. Okay. And so, so here's x, and we put x there. If we kind of bind together the x1 and these frequencies, right, that's essentially the table that's in the book. 0 happens this many times, 1 happens that many times, and so on. And I said to use 7 and 12 for these other ranges up there. And oops, not a terminal. So if I assign it as x is the series of counts. The probabilities, that is the frequency divided by the total. Right? And so those probability numbers 92% have 0, 5% have 1, 1.5% have 2, down to these other ones. Actually, if you plot that, let me make it bigger. Right? Here's 0, 1, 2, 3, 4, and then it jumped to 7, and then 12. These were the probabilities of the different outcomes that are there. So what's the expected value? How many teeth do you expect people to be losing? Zero is the most common value, so the mode or most likely value is 0, right? But what's the mean or average? For probability distributions like this, so the probability, I could put a column over here. In general, you would take the number of zeros divided by n for that probability, the number of ones for that probability, the number of 2s for that probability, number of 3s, numbers of 4s, numbers of 7, numbers of 12. These things should all add up to 1 if the total of all these numbers is n. So expected value, you take the value times the probability, and then add all those up. Right? So take 0 times that, which is 0. 1 times that, 2 times that, 3 times that, 4 times that, 7, and 12. And add all those up, and you get an expected value. So in this problem, if you can do it on computing, then by hand. So here's the values of x. Here's the probability. So I round the probabilities to say a couple decimal places. It's easier to see. So if you take the x times the probabilities, that actually goes component by component and multiplies. And then if you add those up, that is computing our average. So our average is 0.18 teeth, 0.176 teeth. Most are at 0, but there's some 1s and 2s and so on. But that would be the expected number. So in general, for these distributions, the expected value of the number of teeth that's lost is you add up over all the values you can have of that value times the probability that it equals that value. And for these tables, we're taking the number that are in a category over the total to be that probability there. And so this 0.176, right? Teeth. Okay. The units are for teeth because of the counts of teeth. Right? Most are at 0, but some are 1s and 2s, so the average is above 0. So if you went to a different community that maybe didn't have fluoridated drinking water, you could compare. How many teeth lost? Is there a difference between communities with fluoridated drinking water and those without? Or you could go to a community that has not enough dentists, right? You go to a rural area that doesn't have local dentists, so it's harder for people to get dental appointments and get regular cleanings and things like that. Is there more tooth loss in rural areas than in urban areas where there's a lot of dentists concentrated? Could be interesting questions for thinking about the number of teeth lost. Actually, my brother is a pediatric dentist, and when he was at New York University, they would go down to Jamaica, take residents and others, and spend a couple weeks at a school and treat all the children's teeth. So they tried to get in there when the children were just entering primary school, so 4, 5, 6 years old, so they could put sealants on to try to prevent decay of molars. The children that weren't regularly at school, but who would come later, were losing several teeth by the time they were 7, 8 years old. So pretty sad that they were losing that early. So, but anyway, we wrote one paper about relationships of variables in that study. Any other questions? So 235. Let's see. Let's look at one just to kind of go back a little bit. We can look at one problem. Right. So. So this is in involved. Right? So there's a condition called hypoxic respiratory failure. Failure that can affect newborn children. It affects some newborns if they have that condition. It's often enough to supplement with oxygen. ECMO is something called extracorporeal membrane oxidation to save the child's life. So in studies of whether this would work, right, there was a randomized experiment. There was children, they didn't know what to do. Some children died. They stopped processing oxygen, very, very serious case. And so there was a randomization. And some children were treated, and some children were with control. That they were treated with the new procedures versus doing the standard therapy when they would notice this happening. I would presume that they would talk to expectant mothers about this, that they're doing this trial of this new safety, life-saving technology, and if your baby's born, and hopefully not, but if they do have this condition, would you participate in this study? Right. We either give you the standard therapy that we would always do for everybody, or we have this other one that we're trying out that we think is better. Would you agree to participate in this trial? And there'll be some people in placebo or control. We have to do this to try and establish that it really works, right? Before we can recommend that all hospitals do it. So pretty severe outcomes and risks, right? But if you don't do a randomized experiment, you know how you're going to know that you should tell everybody to do it. You might just be getting some good results, and it looks promising, but to kind of prove it so that everybody else should change and they should buy these machines and train people to do it, it needs proof, right? So half and half, the randomized treatment and control. The type of outcome is recorded as positive, right, or negative. It might be death or just damage, right, from. And in the treatment group, the probability. Can I read this? 544. And so 1 minus that 0.456. So 54.4% of the children in the treatment group had a positive outcome. We wrote that as a conditional probability. We made the probability of positive given treatment is 0.544. In the control group, the chance of a positive outcome was 0.364. And so 1 minus that is 0.66. So the way you could write that is the probability of positive given control is the 0.364. So what's the probability in this study of, the question we're going to ask is the phase one, given that there's a positive result, what's the chance that the baby was in the treatment arm? Given that we're all the way down here and we know it's either positive or negative outcome, what's the chance we came from this group or that group? So we're going to reverse the probability of treatment. If they came from that group, given that they had a positive outcome, we're going to reverse the probability. So basically, with all of these things, these types of trees, you can calculate the probability that you're at one of these endpoints by multiplying the probability. 0.5 times 0.544 is 0.272. And this one, 456, is 238. No, 228. And the chance that you're all the way over here, half of the children are in control, and of those, 36.4% are positive, so 0.182 is that probability. And so the negative side, 8.3318 So this one, for example, down here, is the probability that they're in control and they have a negative outcome. Right? Both of those things at once. Put a little separation here. Color. Just gonna get a little separation between these different things out here. So what's the probability? So this phase one, right, we need the probability of a positive outcome. What's the probability of a positive outcome overall? What percent of infants in this study had a positive medical outcome? Based on the table, how do we get that?
You add the two positives together.
Yeah, there's two places that are positive over here, right? This one and this one. These are the probability that we're at these two endpoints. So the chance of positive overall is some of those two places, right? So the probability of positive overall is 0.272 plus 0.182. 454, right? You can always check is that reasonable? 54% here, 36% here. It should be between those two, right? It should be about halfway between because they're half and half, right? And so, so 40. That's right. So the Bayes calculation, by reversing that, the probability that the infant came from the treatment arm, given that they have a positive outcome, is this chance of the treatment and positive out of those that are positive. Right, so 454, the chance of treatment and positive is one of those two arms, right, of the tree, one of these branches. So 272 is that branch. This is treatment positive out of the two that are positive. Sorry, a little photocopy, give me. Let's see. I have to divide that. Get the number. Should that increase or decrease? Should that be more or less than 50%? 272 or 524, 272 or 544. That's 60%. Wow. So there's a slight increase of 50%, right? Slightly more likely to be from treatment than control if there's a positive outcome because the treatments had more positive outcomes, a higher percentage. So if this had been based on a big enough study size, you might have convincing evidence that this is a good procedure, and you could recommend it for general training, general expense, that hospitals should have the machinery to do it, right, and improve care overall. But you need those mothers and parents to agree to that, to be part of that randomization, to have a real clear case, particularly since it's not, it's not like 90%, 10%, right? It's not a slam dunk. You need to have the randomization to convince people. But anyway, that's just a kind of a throwback before this last chapter as one problem. Why don't we stop there on Monday, right? We'll go over that, I said that first set of questions we'll kind of review. If you can look at them all as part of studying. And again, we'll do some questions. I'll hopefully have homework to give back on everything. And, yeah. And if you have a homework 4 paper, don't forget to drop that off.
Okay. But
Oh.
So.
Oh, that's too bad, so.
Yeah, but,
Okay.
so I can consult it as one line item.
Sure, that'd be fine.
So I got sick this week.
Okay.
Pretty far behind.
Okay.
And I know I probably don't deserve full credit, but if I was to get them into you on Monday, like as soon as I walk in.
Yeah, sure. Yeah, let's do that.
Thank you very much.
Okay, thank you.
No, I didn't.
All right, we'll work it out.
Yeah. Been having a little bit of trouble with the hormone filter.
Okay.
Still kind of having a little trouble.
Okay.
Class and all the other stuff.
Do you want to, so I mean, maybe some of the discussion today helped a little bit.
Yeah, I'll explain a lot, but it's, I feel like.
What about you?
Class, it kind of like just doesn't start me for some reason.
So, you know, try to put in time close after class, just kind of going back over things, rewriting the notes and so on. You want to handle this assignment on Monday,
Okay.
right? Take some time to do a little bit more of the problems.
Sorry.
No, that's all right. I think these questions over the weekend, you can also send questions, and I can give a little short.
By how you play, pretty much.
Try to help.
You can't go
I'll
to
take
8 a.m.
the
Saturday
pictures of the
practice.
text
You're
file,
not, like,
so I know what the questions are. I
Yeah.
mean, a couple people are in the same thing, situation. But, you know, do what you can to set things, you know.
Thank you very much.
Thank you.
Have a good weekend.
You too.
Good weekend.
Okay, good.
So I wasn't here Wednesday. I live off campus, so
Uh-huh.
it's hard for me to drive.
Within
back
the,
and
yeah,
forth,
yeah.
so-
Okay, yeah. Well, we get the, you know, the notes are posted, integrity,
Yeah.
and you got a copy of the handout now.
Yeah. Can I get one for Brendan?
Yeah, yeah.
He refuses.
To get up and get out to class.
He refuses to go to Bergeron or like, cause like he has asthma and it gets really bad when it's cold.
Yeah.
And he has like one of those like asthma pumps
Uh-huh.
that he sleeps with when it gets bad. But like sometimes he gets dizzy. So
Oh.
like, but he refuses to go see a doctor. 'Cause he's-
I mean, I encourage you to do that, or,
Right?
you know, has to take care of himself, but, you know, sometimes that, if it's viral, you know, antibiotics or something won't help, but if it's bacterial, then antibiotics can help clear it up pretty fast, and so. If he already has a pump, yeah, that's probably something that needs to be monitored, so, yeah, please do encourage him to take care of himself. You know, he can write me about making up work and getting help, you know, if he has a medical condition that's making it hard for him to do things.
But like he refuses to acknowledge how serious it is.
Yeah.
And it's upsetting.
Okay, well, but please do encourage him to contact me, because I'd be happy to work with him to, you know, make things work out. But if he gets too far behind or is sick and misses the first exam, and, you know, then that's pretty difficult to get back into the course if you're out for a couple weeks. Okay, well, please, you know, let him know that I'm glad to work with him on stuff, so. Okay.